Thanks everyone for joining. So today we'll be discussing magic and RC extraction. And I think the key person here to invite is Tim Edwards from eFabless. So Tim has been working on, it was one of the key person to talk to if you had an issue with any of the tools in the open source community. He started, I think, since 2020 or 19, and I've been working with him a lot initially. So I invited him here to give us an overview of magic and how the RC extraction is done, hopefully a little more on the GF180. Then we'll have a discussion or some simulation done by Stanley, who's a grad student at Michigan, and hopefully we'll have a fruitful discussion today. So I'll hand it over to you, Matt, and thanks for joining us.
Okay, I'll go ahead and share my screen. You can all see my screen?
Yep.
Okay. Yeah, so I last talked to this group, well, a couple times ago, I talked to this group about extraction in magic and some of the research I was doing into trying to figure out how to improve magic's extraction. That was back in August 30. It's been a little over 7 months since then, and I've done a lot of work on that. So it's worth giving an update to that and having a few more details about full RC extraction in magic. So so a little recap on what I talked about back in August. The problem that I had with magic at that time is that it had a simplified model of fringe capacitance in which it was assuming that all fringe capacitance is essentially an infinitesimal area along a line on the border of a metal. And that worked way back in the day when magic was written back in the mid 80s for a 1 or 2 micron process. That was a reasonably good assumption. And since then, it has become increasingly worse assumption. And so as of my presentation last time, I mentioned that I was trying to get a analytical expression, a model for how the parasitic capacitances, the fringe capacitance in particular, is distributed over a halo around the edge of a metal, in which you assume that all of your capacitances are pretty much additive. You can separate out your plate capacitance, which is an easy analytic expression, and then add that to your fringe capacitance and assume that if there is, for instance, here, you've got metal 2 on top, metal 1 on the bottom, and the metal 1 is shielding your capacitance from the substrate, and you can divide the shielded part again between the part of the area capacitance that's shielded and the fringe capacitance that's shielded. So you've got various expressions and coefficients going into your model based on your area, your fringe, and what part is shielding, and so forth. So to expand magic's ability to handle fringe capacitance from this ultra simplified model that it had originally, I started out without knowing a whole lot about how the capacitance was modeled, because I didn't have anything at the time that I could use to model the capacitance. I was trying to work from capacitance tables that were being provided by the foundries, namely Skywater, and figure out exactly what is a good expression to use. So I started out with just a sort of hand-waving argument analytic expression, which I said, okay, it's going to increase the fringe capacitance incident on, say, here from the edge of metal 2 down to metal 1 as metal 1 extends out from underneath metal 2 is going to depend sort of linearly as it extends outward until it reaches some maximum amount, which is the total fringe capacitance. And I had, again, all hand-waving arguments, just modeled this by a sign expression. And so it's very dependent on the halo. I was assuming a constant value for a halo for all metals. And I recognized that this was just a very poor expression anyway, but that was something that got me started to get something that was at least reasonably accurate, certainly better than the original expression. But I actually wanted to model this stuff and get expressions that I could derive from all the modeling. So I started looking at this modeling tool called FasterCap, which is a 3D solver, and I could use that to set up the whole boundary stack up for the, in this case, the Sky 130 process. But I came up with an input file format based on Python, which I could describe any metal stack up with the dielectric layers and the dielectric thicknesses, the metal thickness and height, sidewall dielectrics, all of that could be described in the input structure. And then I had some other Python scripts that would go build out the input files to FasterCap from those structures. So I had a file, and all this is in the I call this a Capiche project, and you can find it on GitHub under this URL, under my name, and the project's name is Capiche. And it has, for instance, a script that will describe a metal layer on top of another layer that is shielding that from substrate. And then you can define the width of the metal, the position of the shielding metal underneath. So I could use that to have, for instance, in this case, where I have metal 2 over metal 1, have metal 1 extending out to something like 40 or 50 microns out to one side, which is effectively infinite. That captures 99.9 something percent of the fringe capacitance on that side. I'll do one test where I have the metal extending out that far on both sides, and I get the total fringe capacitance, or the total capacitance from metal 1 to metal 2. I can subtract out the area capacitance, assuming they're all additive, and then divide the remainder by 2, so I know what the fringe capacitance is, the total fringe on one side, and then from the remainder, I can go figure out exactly how much of the fringe capacitance is incident on the shielding layer underneath, according to FasterCap. So this is what the input file to FasterCap looks like graphically. I've got one metal layer described here. I've got all my dielectrics described, all the values for the dielectrics put in, the substrate underneath. That's what goes into FasterCap. This is a visualization of it. I keep track of all these files in the Capiche project. So I've got this directory called W1SH, meaning one wire over top some shield metal. And then the file name is metal 2, metal 1, which is the wire on top, the shield underneath, the width of the wire on top, and the spacing from the edge of the wire on top out to the edge of the shielding wire underneath. And I create like 100 of these files and simulate each one in FasterCap. And so I can then take the output of FasterCap and graph that out. So when you run the FasterCap top-level Python script, it will generate lots and lots of these graphs. So I looked at this graph for a while and played around with it and with some curve fitting, and decided this is an arctangent, and that for every set of wire coupling, I could come up with a wire over a shield wire. It always came out to be an arctangent, and I could model that accordingly. So I've got 4 wires, 4 curves here. One of them is FasterCap. That's the blue wire. There are a few issues with FasterCap where it likes to switch from like one solution to another solution. And I've talked to the developer of FasterCap. I think I need to do some things where I record the first solution to FasterCap and use that as input to other solutions. So there are various ways that I could probably speed up and make it more accurate. I haven't done that yet. And then an analytic expression where I'm modeling, doing a curve fit to the arctangent, and then a quote analytic simplified where I'm going to show what I did to simplify the expression so that I don't even need to save any particular coefficients. I can figure out what this curve is going to be from all the existing coefficients that I have for other things. And then the one from Magic, the curve from Magic here, is after I've applied all these things, plugged it into the Skyward.
I think, sorry, Tim, to stop you there. I think we have a question from Bora.
Oh, yeah, sure. Go ahead.
Hey, Tim, when device people find a curve like this, they prefer, what I've learned, they prefer to model it as 1 over 1 plus x to the power of n, and then nth root of that. Because floating point processors tend to deal with it faster. than with arctangents and other trig functions.
All right, that's a very interesting result. I was not aware of that, and it's easy enough to go recast that as a 1 over, you said 1 over 1 plus x to the power of n.
Nth root of that. Yeah, so that will give you a different kinds of shapes of this.
Okay, thanks. That explains a lot, because I see that expression, the 1 over 1 plus x to the n, a lot in the caliber expressions that I got from Skywater for this.
Yeah, exactly. It gives you some speed up. I mean, not tremendous, but it does require you know, the microcoded trig thing.
Yeah, that's one thing I wasn't aware of, and it's easy enough to plug another expression in and in place of the arctangent and figure out exactly how much speed up I get out of it. I wouldn't have guessed offhand that the x to the n would be faster than the arctangent. So anyway, thanks. For the purposes of this presentation, I will continue talking about the arctangent, though. Yeah, so this is my replacement function for the partial fringe capacitance. I've got a, using the arctangent, I'm scaling it to 1 over, 0 to 1. So the tangent at infinity is pi over 2. So I multiply the whole thing by 2 over pi. So I get, what I get is a fraction that goes from 0 to 1. And then it's proportional to the arctangent of the distance times some coefficient. Now, I was initially trying to curve fit and figure out, okay, do I need to have this value of alpha, which determines how fast the fringe capacitance falls off? Am I going to need to have a coefficient of that for every single possible combination of this metal over another metal? And what I found out, and I wanted to show all the plots that I made from Capiche to do this, but I didn't have time to prepare those. But what I found was that at least in hand-waving arguments say that, okay, the concentration of the fringe capacitance is going to probably be related to the distance. More accurately, it's going to be related to the distance and the dielectric coefficient. So it is probably therefore related to the area capacitance. Now, since I'm doing the fraction, I'm getting a result which has no dimensionless argument. So if I'm going to relate it to a area capacitance, then it's going to have to be area capacitance for a fixed value of area, like 1 micron squared. And so I plotted that, and indeed it's exact. So I don't need to actually preserve a coefficient for every metal layer. I can derive that coefficient from the area capacitance, and then just multiply it by a scale factor to get the right dimensionless units out of it. And that's, I've been plugging that in. It seems to be very accurate. Certainly gives me answers within a few percent. So that's the current model that I'm using for the fringe capacitance. Now, in addition to that, one of the other things I was fixing in MAGIC was its handling of sidewall capacitance. And also, as I reported back in August, I was implementing the effective near body shielding. So how much of the capacitance to substrate gets shielded by, in this case, I got a metal layer here and another metal layer there. And so there is some amount of that fringe capacitance that's being shielded. For the purpose of doing the sidewall capacitance, I had implemented a routine in MAGIC that would go find the edge, the nearest edge outward from any edge of metal, and then use that those divided down areas to compute what the sidewall capacitance is. But again, looking at the Capiche results, I found that it was pretty much an exact relationship, that if you have a near body wire, that the capacitance, the fringe capacitance, is basically the partial fringe capacitance of that metal 2 down to metal 1 for the distance until it reaches the edge of that shielding near body And then after that, you get essentially zero contribution from the fringe capacitance, so that above the midline here, the total capacitance from metal 2 to metal 1 is the same here as it is here when you extend metal 1, and no matter how far off you extend the metal. So using that same expression for dividing up, or the same routine for dividing up the areas for the sidewall capacitance, I could use that same routine to say, all right, this is the area that is essentially a partial capacitance for the fringe from metal down to substrate, and everything behind it is completely shielded. And I subtract that off from the total capacitance to substrate. And again, that works, and that actually saves some coding from what I had before. So I was previously actually calculating the effect of the near body, and now I simply just don't compute the fringe capacitance beyond the near body and its equivalent. So I actually sped up the calculations a bit that way. So that's the state of the Magic's routines for calculating fringe and all types of parasitic capacitance. My issues right now is whether I have all the information I need to plug into Capiche to give me all of the coefficients I need out of it. GF is very good. It has given me not only a stack up in the open source documentation, but stack up plus the deltas for the high and low corners. Sky 130 doesn't have the deltas for the high and low corners. It does have some capacitor tables at high and low corners. So if I want to redo all the calculations for the corners, I probably need to figure out how to back calculate the layer and height deltas for the corners from those capacitance tables, which is going to be something of a bit of a pain. But once you have those values, all the just running Capiche is a pretty much automated process, and I can just crank out the coefficients that I need for Magic. And I think Stanley will give some results that appears that it's getting reasonably good results. So I think it's supposed to be within a few % of what you could get out of commercial tools, and that seems to be the case. So onward to the full RC parasitic extraction. This is the fairly lengthy set of commands and Magic that you need to do a full RC extraction. I am still at the state where I don't trust what it does if it's hierarchical. And so I recommend that you flatten the cell before you do a full RC extraction. I've been able to do full RC extraction on some fairly large circuits. So I did one on a 1 kilobyte SRAM from the OpenRAM project, and was actually able to get a meaningful result out of that, although the thing was at least 100 megabytes SPICE, and I tried simulating it in NG SPICE for several days, and it never really started up the transients. So I have some work to do to figure out how to get something like that to simulate. Magic's algorithm for the resistance extraction has been in there for quite some time. I think it dates back to around 1990, maybe, if not before. But it's fairly straightforward. What it's doing is it's going through all of the geometry, sort of a 3-step process. The first step is to figure out where are your drains and sources, all the terminals of any device. So find your drains, your gates, your sources, your substrates, and your drive points, which would be like a pin. And then from that, determine which way the current is flowing. And once you've got all that information, you can overlay your geometry with some directed graph that says, okay, this is the way the current is flowing through each of these wires. And then from that, figure out what's the wire geometry, what's the width and length, and come up with resistance. And once you've got this graph of resistances, then you can run it through a simplification in which you combine resistors in series and parallel until you've got a fairly simplified expression where you've just got internal nodes where your resistors are branching, terminals where you land on a device source or drain or a pin, and hopefully just a single resistor in between those. So I've been trying to figure out, obviously this is a set of code that somebody wrote a long time ago, and I've sort of been trying to figure out, is it valid? Is it still valid? So I've been running the full RC extraction. This is the SRAM, well, one of the SRAMs. This isn't the 1K SRAM, but Matt Goodhouse sent me this little tiny SRAM, which has just like I don't know, like a 8x8 or something set of cells. And it's small enough that I can extract the thing in a few seconds. So it's fairly easy to work with and doesn't take all day to do extractions. So I've been spot checking by saying, okay, well, look, here's some kind of long line in here. Now, what is Magic's RC extraction producing for that? So sorry, going back, like looking at this top corner here, zooming in on that, I've got this input coming in from a wire going into an inverter. It's got this long poly line going between a fairly widely separated NMOS and PMOS. So I can do a hand calculation on that. This poly line going from the center point out to the NFET is like about 18 squares of poly, and poly is 48.2 ohms per square in the Sky 130 process. So that comes out to about 888 ohms. And if I look in Magic's SPICE file or the .res.x file, which is its internal extraction format, it says that that line is about 900 ohms, which is in fact about 888 plus, counting this little tab of poly where it connects out to the center point. So it, just doing basic spot checks of wires, it looks like the answer is valid. I have not yet seen anything that would suggest that it's producing invalid results. Now, Stanley is going to give a counterpoint to that. So there is probably plenty of investigation to do. There are many ways that this could be going wrong. The main way it would be going wrong is if it fails to determine which direction the current is flowing, you could get a wildly incorrect answer for any segment of your graph. As I said, in my spot checks, I haven't found that out yet, but if I have some counterexamples to work with, I'll definitely investigate. If Magic is not producing the right answer, it's my goal to make sure it does. So anyway, that is my presentation for where the state of things are right now, and thanks for listening. We can either go on to Stanley's presentation right now, or I can take questions and answers now.
Yeah, let's see if there's any questions. Thanks, Tim, for the presentation. Are there any questions for Tim?
Yeah, I can send you some actually good-looking SRAMs if you would like. I have this. I mean, it's really. I mean, this is a Sky 130 1 KB SRAM, and the key thing there is this does have a timing replica that needs to be correct. We can perhaps, I mean, we certainly did this with commercial tools, but you can try to correlate that with Magic and see how it looks like.
Yeah, I would love to have.
This is assembled by, this is a custom memory generator that we built from scratch. The extraction here and simulation have been done by using commercial tools. The idea here is, can we correlate what we see in commercial tools with what you see in Magic?
Just a question, Bora, is this available on GitHub for people to review, or?
We are not advertising this yet. It is available on GitHub, but it is buried. We are not advertising because we are waiting for silicon
I see.
to come back. We don't want to put things out that will mislead somebody to
Sure, understand
that this actually works if we don't know if it works.
Yeah, so it's you're saying this is a compiler, right?
I would call it a generator.
A generator. Good. Okay, well, thanks for sharing. Yeah, so there's a bunch of things I wanted to mention here, which are basically having some test structures to help the work done by team here, but also there's Matthias from K-Layout. I don't think his mic is working for some reason, but basically developing tiles so people can have silicon data like on simple structures and then correlate with whatever models team is using could be very beneficial, and it will help us close the loop between design and technology and models, and basically decouple all the issues we've been seeing with these open source tools. Yeah, so are there any other questions, or should we move to Stanley's presentation? All right, I guess not. So Stanley, do you want to share your screen and present?
Okay.
Thank you.
Okay.
So just to give some background here, this is an Opamp we designed for a different project. And when we were closing the design, we noticed some discrepancies. So we started, the Opamp isn't really a good way to see if there are discrepancies, but I have asked Stanley to make simple structures, and he will show that at the end of the presentation. So just a little bit of background here. So go ahead, Stanley.
Okay, thank you. So thank you for having me to give this short presentation. So what I've done is based on our Opamp in GF180. In order to see the actual simulation result, we again ran the simulation on the closed tool. So in my presentation, I will first introduce our circuits and show you the comparison results, and then I try to do some preliminary checking for some simple circuits, and I will show you in the end of the presentation. So first, our circuit is a two-stage folded Cascode Class AB Opamp. And so the functionality of this Opamp is basically you can change the VPROC, and then you can get different gain, different bandwidth, and different noise performance under different power. And this is the layout of our Opamp. So I extract the Parasitic from both tools, closed tool and open source tool, to see if there is any discrepancies. So this is the Parasitic Extraction command I use in Magic. I think Tim just mentioned this, so I'll skip this part. And this is the capacitance comparison between these two tools, and you can see the value of capacitance on at least some nodes coupling capacitance here, and you can see at some nodes there might be a large discrepancy. And this is the total resistance. So in the beginning, I used Python script to sum up the resistance on the specific node, but it turns out that this total resistance might not be correct because the way I calculate the resistance might be incorrect. So the problem is that when I use the Python script to sum up the resistance in the same node, so for example, this circuit showing below, the ideal value should be R in parallel with 3R, but in my script, I just sum up these resistance. So the total resistance showing in my Python script would be 4R. So for now, I think for me, it's hard to analyze the total resistance on the complicated layout because you don't know the parasitic resistance would be. Some resistance is in parallel with some other resistance in series. So yeah, for now, I'm hard to analyze the real total resistance for a complicated layout. Okay, so let's go to the simulation results. And this is the test bench I use for our Opamp. So it's basically with a DC feedback to set up the output voltage common mode. And this is the pre-layout simulation result. You can see almost all the performance are the same between the closed tool and the open source tool. And this is a post layout simulation table. You can see there is some discrepancy shows up, and this so there are like a few percent of the difference, and which is due to the different parasitic extracted from both tools. Okay, so I list the increased percent of difference between the pre-layout simulation and post-layout simulation. And so, yeah, so it's a summary for the simulation I just mentioned. So in pre-layout, there are almost no difference, but in post-layout, this difference shows up because the discrepancy in of the extracted is from both tools. And so, yeah, that's basically the result for our Opamp. And I actually run a different test bench on the Opamp, which is the unit gain feedback. And I think I will just quickly run through these slides because this is similar with the simulation I just presented. Yeah, so this is pre-layout simulation, and you can see just like the previous one, almost all the performance are similar. And this is the post-layout simulation. So you can still see some difference caused by the discrepancy. And so I want to mention the gain error here. So the gain error means that, so for example, in this test bench, the ideal gain should be 1 because this is a unit gain bandwidth. So the gain error is basically means that how much gain is shift from the ideal gain, which is 1. So you can see the gain error is very small for this Opamp because this gain error comes from the open loop, the finite gain of the Opamp. So if the ideal Opamp with an infinite gain, the gain error should be 0%. But because our Opamp has finite gain, so we have some small gain error. And why is the gain error so small is because that our loop gain is very large, even beyond 100 dB, and 100 dB open loop gain can actually give you this less than 1 micro% gain error. But you can see the gain error between a closed tool and open source tool is kind of large, like 30%. That is because how we calculate it. Like if the gain has a little bit, open loop gain has a little bit change, that will give you a large gain error difference. Yeah, and these are the figures for the Opamp. And so I put the Bode plot and noise plot here versus frequency. And this is the gain vs power and bandwidth vs power. Just like I said, our functionality of the Opamp is basically on the gain, bandwidth, noise, and power trade-off Opamps, which means that you can operate the Opamp under different power and you can get different gain. So this the pre-layout figures. You can see that the gain and bandwidth actually increases when the power increases. And this is the phase margin and noise. You can see the noise, especially for the noise. When you increase the power, you can get lower noise. So that is basically the function of this Opamp. And so this is the layout. Okay, so this is the step response for this unit gain feedback bandwidth. So you can see that the Opamp is stable. Okay, so I just quickly run through all the figures, and this is the post layout step response, and post layout gain error vs power, and bandwidth vs power, noise vs power. Okay, so and in this appendix too, I will show you a partial screenshot of the circuit netlist. So this is the pre-layout circuit netlist. So in this slide, I want to show you that there is some something in ngSpice, which is the maximum of the total width is 100 micrometer in ngSpice. So if you have a large device, we use a large device in Opamp. So if you have a large device beyond 100 micro, you have to put that put those devices in parallel. So so in ngSpice, the 4 micrometer, if you write, if you have a line with 4 micrometer and with finger equals to 4, that will give you some error messages. ngSpice will show you there is something happens in your in this line. And this is an extracted netlist from the closed tool and open source tool. So you can see, just like the general netlist, there is a bunch of R and C there. And then I run the extraction. Here is some extraction examples. So first example is a simple common source amplifier, which is showing here. So this is a N MOSFET with a passive load, and on the right side is its layout. So I first extracted the netlist from Magic. So in the middle is the exact netlist extracted from Magic, and I manually convert this netlist to the schematic on the right. So you can see here is some parasitic resistance in series and the capacitance on each node. Okay, so then I try to extract the netlist in closed tool, and I show you the partial netlist because the netlist generated from the closed tool is way more complicated comparing to the netlist generated from Magic. And so for this closed tool, fortunately, it's not much more it's not complicated compared to the Opamp, because Opamp is has a complicated layout, and this is just a simple common source. So I'm able to combine all the resistance in series and in parallel and calculate the resistance between each node, and then I converted it to a schematic. So let's compare the schematic from the Magic and from the closed tool. So so these two schematics is showing here. So actually I simplified the previous schematic. So yeah, I try to like combine again the resistance in series and parallel and calculate value and combine the capacitance in parallel. So here is the result of these parasitic value. So you can see the closed tool actually has a larger parasitic, and it's so for the both R and C. So then I run the simulation on this common source amplifier, and the test bench is showing above. So I drive the input with a voltage source, and then this amplifier will drive a 20 femtofarad loading. So in the pre-layout simulation, it is almost the same, but the post-layout simulation, some difference shows up, and you can see that the result from ngSpice is actually the bandwidth from the ngSpice is actually larger than closed tool, and which meets our observation here, because the closed tool has a larger parasitic, so might have a lower bandwidth, and these discrepancies will give you 3.9% of difference on the bandwidth between both tools. Okay, so next I will show you the second examples, which is an inverter. So this is a schematic of an inverter, and on the right side is the layout of this inverter. So I use the same steps to analyze the parasitic resistance and capacitance, and just like the common source amplifier, this inverter has a not much complicated netlist, so I'm able to calculate all the resistance and capacitance here. So compare with the schematic from Magic, the schematic from the closed tool actually has a larger parasitic, just like the common source amplifier shows. So especially on the input to output path. So with these larger parasitic, it is expected that the Magic, the simulation in the closed tool will have a lower speed. And exactly. The simulation results is shown here. In the pre-layout simulation, it's very similar, but in the post-layout simulation, both fall delay and rise delay, NGSpice has less fall delay and rise delay, and it will give us around 4.6% difference. So, and in order to, so I simulate again with a different loading. So in this slide, I replaced the 20 femto to 2 femto to see how does the circuit change, how does the simulation result change due to the loading, the value of loading changes. So actually, so you can see a larger difference when I replace the loading with a smaller one. So it will give us like 8.8% of difference between open source tool and closed tool. Yes, and that's my presentation. Thank you for listening.
All right, thank you, Stanley. Great job. Dan, yep, Dan has a question.
Yeah, great work. The I mean, it does point that this is going to be an uphill battle to build trust in any of these tools, right? They have, certainly as compared to the ones where the foundry is responsible for the rule deck that goes into them and, you know, commits to supporting an extraction deck in a particular tool. And I think you guys have the right, and generally requires a lot of silicon and a lot of kind of calibration and testing to sort of get it right. And I think you guys have the right approach in kind of bootstrapping on the existing, you know, foundry decks and existing tools. Maybe we'll hear about some silicon measurement efforts, but I think the other software is probably going to be the much less laborious route. But I think what some of the last presentation brings up is it's pretty tough to even find the right comparisons to make to deem these things good enough or apples to apples, right? It's not really a reasonable level to say like the whole Netlist is identical between two of these tools. Plus they have lots of settings and lots of configuration that may or may not be relevant for any given circuit. So I think it does have to be these kind of circuit level things, and we have to be smart in selecting which ones to go after. So this is a thought more than a question, but it would be great if we could compile some of those and find some more means of sharing them, right? Some means of saying, these are kind of the important test circuits. Some of them will be just kind of geometry. Some of them will have devices and
I agree with that, Dan. I think Michael earlier was basically to see if there's anyone in the group who wants to help us define these test structures. I mean, obviously some of them are very obvious, but getting some expertise there, especially from the model folks or you know, any other members who wants to contribute, please reach out, and we'll definitely make test structures. We made some of them in MPW5 in Skywater, and hopefully we'll make some on GF. But if
hey, Maddie.
Yep, go ahead, Rob.
Yeah, it's Rob. So has anyone talked to Global Foundries or Skywater to see if they have test structures that they might be willing to put out in the open source community, aside from, you know, design folks?
So I'll let Tim Edwards talk more about it. But in Skywater, we got some proprietary test style, and we made an open source version of it. But in GF, I'm pretty sure they have data and the measurement data and test styles as well, right? So
yeah, we're getting the test data back slowly, but yeah, we haven't been able to get Skywater to open source much of anything from their test structures, but we have the test structures, the ones that Mehdi made.
Okay, I was just curious. I think Dan's comments were spot on. I mean, I know in general, you know, in Spark engineering and also back in IBM, right, we would do test circuits that would then go into test wafers, right, that we would then get measurements on and then use that to help calibrate the tools or upgrade the algorithms as needed. Okay, thank you.
So Tim, just clarifying here, did you get the MPW5 test structures, or is there some other structures you're talking about?
Well, going back to, you had some stuff on MPW2, right?
Yes, I did. Yep.
Yeah.
Okay.
Mhm.
Okay.
Yeah, we haven't had anything more recent than that.
Sounds good. Yeah. I don't know, Boris, do you have any comments, or since you reviewed this work as well? Not sure if you were there.
Well, Bora has his hand raised.
Oh, okay. Bora.
Yeah, Dan had it spot on. And just to add to that, anecdotally, we were looking at this at some point. You know, we did some variability studies, and in other processes 15 years ago or so. And you know, then we were made aware of the structures that commercial industry uses to you know, calibrate caliber and other tools. They're fairly elaborate. You know, we have seen some of that under the NDA, and you know, it is a large suite of things that tries to isolate different kinds of parameters that go into both spice and interconnect modeling. What I was told after that is that in order to validate that, you need about 20 lots to, you know, to actually populate a caliber model, and that costs quite a bit of money. And then, you know, quite a bit of a processing time after that. So the question here is, you know, what would be the minimum? You know, I'm assuming that we don't have funding to develop that kind of a test structure that would compete with Caliber. And by the way, either other vendors have a hard time competing with Mentor in that space. First, you know, developing that kind of a test structure, along with funding, you know, a smaller part of that are these 20 lots. The question here is, and that's also, these 20 lots were cited with respect to qualifying SRAM, a different type of an SRAM. You know, extraction associated with SRAM parasitics. The question here is, what is the minimum set that we need, and how do we get to that minimum set? I know who has thoughts about that.
Just to clarify, thanks, Bora. So just to clarify, you're talking about the test structure's minimum set, right?
I'm talking about the minimum set of test structures and the minimum number of wafer runs that we need to qualify that.
Yeah, that's a good question.
Well, it being open source, I would take the approach of assuming that this is an ongoing thing and that we will use as many tape outs as we have, just throw some test structures on every tape out, and then after a while, your tools get better because your results get better.
Yeah, I think that's the best we can do right now, which is basically reusing this the test structures we made. One thing we can do is improve them, and getting feedback from the community would be great. We put them on GitHub. I'm happy to share them again. And but yeah, Tim, if there's any way we could help you to improve the models or the extraction process in Magic, then we should probably discuss that as well, because it's unclear to me how which type of structures can help you improve the current extraction results.
Well, anything that shows a discrepancy of around 10% or so or more is going to be helpful, because it's something I can look in and immediately see what the problem is. I would like to knock down the discrepancies to under 5% in all cases if I can.
Sure.
So something like this. And in fact, this is sort of expected. I do know that there are, the one issue that I've seen in the resistance extraction is that sometimes Magic is ignoring things, ignoring stack contacts. I think there's a problem there where it's not properly decomposing the stack contacts into individual contacts, and it's occasionally missing them.
Sure. So we do have a question from Matthias. Sorry.
Yeah, go ahead.
Yeah, so he's asking the same question: what are the test structures that are intended, and did anyone create a fast cap model so far for comparison or calibration?
Well, I did the faster cap model, which is a 2D model of the foundry process, which is reasonably good for most calculations. Could be better with a fast cap 3D model, I think. But I haven't attempted that.
Okay, so
To add
yeah.
to things that I was mentioning, so IBM at some point, maybe about 10-ish years ago or so, when they were getting out of this business, published some of unusual or less common test structures that they were using. It is worth looking at that. I can try. I believe it's Keith Jenkins who retired soon afterwards. Went on publishing. I mean, basically, IBM did not open source them because there was no way of open sourcing them, but they went out and published at several venues structures that they were using for extraction. That's something that is worth looking at. Again, I repeat, those are uncommon ways. Some of the less common structures, more of IBM style.
Sure. I think Christian Enz from EPFL mentioned he has some test structures we could reuse, but those were more tuned toward modeling. So we'll look back with him as well. But if you can share any link, Bora, that would be great. All right.
Yeah, any set at this point is a good set to start off with. So anything you could throw at and put into a single repository and say, okay, here's a start, that's going to help.
Sure. Okay. Any other questions or comments? All right. So in any case, in the background, we are trying to put together proposals and the work to be done here. So please remember to reach out if you have some ideas or resources we can use for this this work here. And I think in the future, this is going to be an automated process where we can reproduce it in different technologies that are going to be open source, hopefully. So let's see. All right. Thanks, everyone. Thanks for joining, and have a nice day. Thanks, Tim.
Okay, thank you
Stanley.
very much. Appreciate it.
Thank you.
Bye-bye.
Mhm.